Welcome to this IEooc lecture on steel. Steel is the world's most widely used metal. About half of it goes into buildings and infrastructure, and other large quantities into electrical machinery, mechanical machinery, products like packaging, vehicles, or appliances. In total, we produce more than 5 million tons of steel, but not per year or per month, but actually per day. So if you look at the ratios to the other metals, you see that steel or iron production is much larger than all the rest of the metals combined, like copper, aluminium, or manganese. And many of the other metals are actually used as steel alloying elements to make it stainless, for example, like chromium or vanadium. So how is steel produced? The most common production from natural resources happens via the blast furnace. You see such a huge industrial facility on the left side. Here, the iron ore, the purified ore, iron oxide, reacts with carbon monoxide from coke to liquid iron and carbon dioxide. The result is pig iron, which is an alloy of iron and carbon. And to get good properties like moldability or the ability to roll it out to flat sheets, the carbon content needs to be reduced. So the pig iron is sent to a so-called basic oxygen furnace, where a ladle is inserted with oxygen blown into the liquid pig iron so that the carbon oxidizes first, and as a result you have a more pure iron alloy, where you could also add slag formers to reduce phosphorus and sulfur content, and you could add alloying elements. On the right side, you then see the so-called continuous casting process that is predominantly used to cast the liquid steel from the basic oxygen furnace into shape. And as the liquid metal is poured into the mold, it solidifies from the outside and is drawn out into the rolling mill to form so-called steel slabs, of which you see one here in this picture. So this is what we call primary production route, primary from natural resources. The steel is then rolled to flat or long products, cut into shape, and then it's cooling down. And you can have the rebars, the steel girders, the sheet metal from which you get the appliances or the vehicles or the buildings. You can, when you have some time, watch this video of vehicle manufacturing where you actually see the steel coils being cut, stamped, formed and welded together to form the body in white of the different vehicles. Now, the different stages of using steel all have their losses. In the rolling mill, you have the so-called mill scale, the semi-oxidized steel parts that fall off the glowing hot iron. There may be off-spec material. There are trimmings, there's machining swarf, there is sawdust, or there are trimmings also from deep drawing. So all of these losses occur in the steel mills already or in the manufacturing process. And these pre-consumer losses can be substantial. And usually this material is sent to remelting as so-called new scrap or fabrication scrap, because it is often of high quality and it comes in large and defined quantities. So you see here from the book With Both Eyes Open on Aluminium and Steel Sustainability by Julian Allwood and team, how much loss there actually is. So if you go from the right side here, you start with 1 ton of liquid steel, and then you have the processes accumulating losses through the manufacturing, from liquid steel to hot rolled, cold rolled, galvanized coil to blank coil, and finally to the stamped panels. You have for an I-beam used in buildings about 10% loss, and you have for a car door panel more than 50% loss, mostly due to the trimmings, but also losses in the rolling mill. So collecting the scrap and maybe finding better ways of manufacturing to reduce the scrap are main strategy to improve the material efficiency in using steel and also other metals. So steel is mostly used in construction. It actually forms the backbone of modern societies. The infrastructure, the bridges, the buildings, the factories, water pipes, all of this is made of steel. The same holds for vehicles. Many vehicles, from the bicycle, motorcycles, trucks, buses, and cars, contain large amounts of steel. Once these products reach the end of life, and this can happen quickly, for example, a steel can, packaging can for canned food, has a lifetime of a few months, or it can take 2 centuries for a steel bridge, for example. But once the steel product reaches the end of life, it turns into scrap. And the scrap is remelted via the so-called secondary production route. Secondary because it doesn't use the primary natural resources, but the secondary resources from urban mining, or more mundanely spoken, the scrap. The scrap is sent to electric arc furnaces. You see one here, and it's remelted there. You span the electric arc between the carbon electrodes that come from the top and that are connected to the high voltage grid, and the steel that itself conducts electricity, and also the molten bath or liquid steel below. And here, at very high temperatures, far below 2000 degrees Celsius, the steel scrap melts. You add slag formation to adjust the alloying composition of the melted steel, and then you tap out this molten steel and pour it into shape with a continuous casting process in the same fashion as we would do in the primary production route. The result looks as follows. Here we have a very detailed Sankey diagrams of the different steel sources, primary and secondary, iron ore or scrap, the different steel shapes. This is the purple colors here, the slabs, the ingots, the billets, and the different semi-finished products, the wire rods, the hot rolled coil, and so on. And finally, the finished applications, the vehicles, industrial equipment, the constructions, and the metal goods. This work was compiled more than 10 years ago by John Cullen and team. It is still the most detailed picture of the global steel cycle today. And of course, it is only a static snapshot here from a given year. Every year, the steel cycle changes. In every country, it looks differently. So we use a lot of effort in our field to understand first the flows of steel, then their qualities, and then assess their recycling or emission savings or energy savings potential. So here is a more recent example by Takuma Matari, who analyzed the steel cycle at a similar high level of resolution in 30 different countries. To identify types of countries, there are the import-dependent countries, there are the net scrap supplying countries, and so on. So all the different countries play their specific role in the global steel cycle, which is crucial if you want to understand the sustainability transformation in the steel cycle. You have to know, for example, how much scrap is available, how large are the stocks, how fast are the stocks growing, and so on. So all of these things need to be known to first make scenarios for future steel demand and then link them to energy and emissions. One problem in the steel cycle is that we have limits to recycling. There are irreversible losses at all stages of the cycle. For example, we have dissipative use. Some steel products rust away. Some products turn into obsolete stocks. They are non-recoverable, for example, pipes buried deep underneath other buildings or infrastructure. It's too costly or sometimes not possible to recover. So we have some losses here. We have shredder residues or missorted metals, steel that ends up in landfills, steels that end up in slag piles, and so on. So there are always some losses due to missorting or imperfect sorting in the end-of-life management streams. We also have Remelting losses. Once you heat up the steel to more than 1500 degrees, there is some oxidation of the steel going on. That's unavoidable. Typically, about 5% of the iron are oxidized during the remelting process. For some alloying elements that are less noble than iron, it's even more. And the reason is that the quality of the melt matters more than the total yield of the process. So we accept that some losses happen at the remelting stage, which means that strategies that avoid remelting, like reuse, lifetime extension, or remanufacturing, have an additional benefit. They reduce the loss in the recycling loop, and at the same time also they save the energy of the remelting. Overall, we observe cascading, or sometimes called downcycling, in the steel cycle. This means the quality of the recycled steel isn't generally lower than the quality of the steel from primary production, so it's shifted to applications that demand less quality. And the most common shift in the steel cycle is the shift from sheet metal to long products. So the primary steel is often used for sheet metals to turn them into cars or washing machines, and the end-of-life scrap from these products is remelted and turned into long products like I-beams or concrete reinforcement bars that have a higher tolerance against impurities from the recycling process, especially copper or tin as so-called tramp elements. And the reason simply is that these products don't need to be rolled out to very thin sheet metal. The thinner you get, the easier it is that things get brittle, or you get cracks, or the stability isn't high enough. For long products, that's not such a big problem. First of all, they're not very thin, so you don't have the cracking problem. And second, in case the quality is a bit lower, you can simply make them a bit thicker and it will be fine. This is not possible for sheet metal, of course, which has to be thin so that the car weight or the washing machine's weight is in a reasonable and acceptable range. What is the consequence of the different losses in the steel cycle? One analysis was conducted by myself a few years ago. You see here a model of a steel cycle running for more than a century. Into this model, we insert a certain quantity of steel, here in form of a vehicle, in the year 2015, and then we let the model run over time and we trace the steel through its different application. On the left side, you see the current standard case. First, in 2015, 1 ton of steel is put into a vehicle, and then you see the slow decline. It's like an S-shaped curve, which is the lifetime of the cars, typically 20 years across the different vehicle types. And then the end-of-life scrap enters the waste management streams, and from there it's mostly recycled into construction. This is the yellow section, and some ends in losses. You see here the different recovery losses, remelting losses. They happen. And once the scrap is remelted into construction steel, it stays there because the buildings have a very long lifetime. So here we see an interesting trade-off in the steel cycle. If we move to the right plot, in the right plot, we model a closed loop steel economy. Closed loop means we keep the steel in high quality applications. So it's a scenario where we don't cascade the steel into construction steel, but keep it in sheet metal form for machinery and for vehicles. But what happens? First of all, you see the desired effect that the steel stays in high quality applications for a longer time. It's orange and the blue section. So this is good, but because these applications have a shorter lifetime, we have higher losses. So we have a trade-off here in the steel cycle. We can keep the steel longer in high quality applications, but at the expense of higher losses. Whereas in the conventional downcycling situation, we have lower losses because of the long building lifetimes, but also lower quality applications. So you see, circular economy in the steel cycle is not trivial, it's not easy. There are unavoidable losses. These losses can grow larger if we keep steel in short-lived application and do a lot of remelting. And there's a trade-off between long-lived but low-quality construction steel and high-quality but rather short-lived sheet metal. We can extend the steel cycle model for even longer times. Here I had a dynamic MFA model running until the year 3000, so 1,000 years from now. Keeping steel cycle parameters constant, we see the slow decline. So it's an extrapolation of the curves from the previous slide. We see the slow decline of the in-use stocks of steel, or originally 1 ton, over time. And from this graph, we can calculate the area under these curves, and this area corresponds to the lifetime, the average lifetime of the steel in the anthroposphere. And you see the typical applications as we have them today. We have an average lifetime that ranges from 250 to maybe 360 years, the blue and green curves. So this is the average lifetime of an iron atom in a steel alloy in the anthroposphere. If we do closed loop, it's actually shorter for the reasons I mentioned below. And if we go straight into buildings with a lot of circular economy, it can extend up to 560 years. So overall, steel lasts for centuries in the anthroposphere. That sounds like a lot, but remember, the environmental damage of the steel, especially the climate impact, will last for millennia. So it's maybe not that sustainable after all. So we need to really look for methods to reduce the carbon implications of steel manufacturing and still keep it in use for much longer, as we would do it with today's parameter settings of the steel cycle. This is, of course, well known by the industry. So you see a lot of fancy reports out there. For example, here the Sustainable Steel Report from the World Steel Association, where they list all the benefits of steel that I have also reported in this lecture. And they also report on the major sustainability challenges in the steel cycle and the steel industry. There is the co-product challenge, there is the responsible sourcing challenge, right, the mining impacts and so on, and of course the climate change. I think the most important message here is hidden in the small print in this report. It is down there. If you zoom into this, it says that if you want to produce 1 ton of steel, you will emit about 1.8 tons of CO2 in this primary blast furnace road that I explained before. And if you take these huge quantities, 5 million tons of steel per day, you will see that about 8% of all CO2 emissions come from the steel industry. So only making this one material accounts for 8% of global emissions. No car is driven, no building is heated or cooled, just putting the material into place, 8% of CO2 alone. So we have to address this problem. CO2 is definitely the dominant challenge that we have for the sustainability transformation of the steel industry. It's not the only challenge, right? There is maybe pollution of air, there is the land use of the mines and so on, but the carbon challenge is the one that matters most. If you take steel emissions and put them into the country ranking, you would see that steel emissions are about as large as the emissions of entire India, maybe half of US emissions. So steel is a major industrial emitters. If you look at it as a country, the steel industry, it's in the top 5. And we know that these emissions from material production really emerge as a major bottleneck to curbing global warming. Why is this the case? Well, first, it's because they're growing. We need more materials, especially also more copper and other metals for the energy transition, but also more steel. And these emissions are difficult to mitigate. Why? Because you have to rebuild the entire industry from moving away from coal, maybe using hydrogen as a reduction agent. That doesn't happen overnight. That takes decades and huge investments and a lot of political commitment. So we look at the circular economy as a vision for sustainable material cycles also for steel. Next to Shifting the fuel, for example, from coal to hydrogen, we also need to address the problem of ever-growing stocks in the circular economy. What you see here is the ratio of stock change through inflow, through consumption across countries and years. What does this equation tell us? It tells us that every inflow, every consumption of steel either replaces outflow, so when you replace an old building, or it expands the stock, greenfield, right? If you have a new city, you need to put in the steel into the use phase in the first place. And we see that countries at the different stages of economic development have different ratios of stock expansion to inflow versus maintenance to inflow. Countries like China or Indonesia or Egypt, they are close to 100%, meaning almost all of their steel consumption goes into stock change, expanding stocks. Countries with mature stocks like UK or USA or Japan have much lower ratios. This means that 100% minus this share, this is the outflow over the inflow according to the equation on the left. This share goes into maintaining stocks. So some countries are close to zero or even below zeros because their steel stocks have stabilized or slightly shrinking. In this case, only in this case, you can have the chance of a circular economy. If you are in a situation like China today, or also Brazil or Mexico, where most of your consumption goes into expanding stocks, you cannot recycle because there is nothing there to recycle from. You need to put the stocks into place in the first place. This is, of course, a major commitment also in emissions, and only in later decades, in the second half of the centuries, these countries that are currently green or red could move down to more bluish shaped trajectories where most of the steel is then used for replacing outflow, giving them a chance to actually use that outflow to recycle it into a new inflow of steel. And we see these country-specific patterns. Here by Takuma Watari already mentioned, we have, for example, mature economies with high recycled content and abundant scrap. The USA, for example, you see here the circular flow is large. Lots of recycling is happening, more recycling than primary production, lots of EAF steel, electric arc furnaces, mostly going into flat products, some long products, and then back into the use phase. But you also see countries like China, where of course recycling is growing, but still they are mostly reliant on external imports and mining of iron ore, primary production, to expand the stocks that will enable them to recycle in a few decades from now. Overall, we can see that the circular economy has different loops of getting the steel, once it's not used anymore, back into new applications. There's the maintenance and repair loop that could lead to longer vehicle lifetime or longer building lifetime, and this would avoid remelting the steel scrap in the first place. The same holds for reuse or remanufacturing. So steel sheets could be taken out of the building and maybe cut or welded into new construction shapes. And only once this is not possible, the circular economy would allow for recycling, which in the case of steel means recycling with unavoidable quality losses and remelting losses. And the reality check for the circular economy is done by the industrial ecology models of the steel cycle that are maintained and developed in many different research groups in different countries, and it increasingly get the detail that is needed for getting good policy and industry decisions, for example, by considering different quality grades of steel. So in those scenario models of the steel cycles, we include these different circular economy strategies: the narrow strategies, the slowing and the closing strategies. There is a lot of things that can be done: longer lifetime, better recycling, reuse of fabrication scrap, and so on. So for vehicles, for example, the list of circular economy strategies is long, right? Take a moment here to look at these strategies. Everything from using cars more efficiently so that you need less cars because the individual car is driven for longer, to component reuse, to downsizing, to better recycling is possible. Similar for buildings, right? You could go all the way to the narrow strategies, using less building space in the first place, all the way to longer building lifetimes or better reuse of construction steel instead of remelting it, because in buildings, most steel components are only used under static loading, not dynamic loading, so they have a much longer lifetime before they start to get brittle or lose strength. We put these strategies into the steel cycle models as parameter changes. In the future, all of these processes have their process parameters, the energy demand, the process yield, the lifetime, and we change those parameters in line with the circular economy strategy potentials that we have sourced from the literature. And the results are plots like this, where we can plot the mitigation wedges of the different strategies over time. So if we don't do anything in terms of circular economy in the global steel cycle, we will get the blue curve on the top in terms of global emissions from the steel cycle. And it's roughly flat if you look at it from the distance across the next 30 years. Why is it flat? Because overall demand will flatten after the huge construction boom in China. Industry is getting more efficient and slowly some recycling happening in larger quantities and some emissions mitigations happening. So the baseline is not not a disaster, right? It stabilizes at high levels even if we do nothing about sustainability. But we need to do more in terms of climate protection if we want to be serious about the 2 degrees and 1.5 degrees Celsius target. And this you are here shown on the right side. We compare the global steel cycle's performance with the average industrial performance across the globe, linking it to a temperature range of global warming. And you see, to go down to lower ranges of global warming, we need to kind of switch on additional strategies. There needs to be more energy efficiency in industry. There needs to be more material efficiency in the industry. For example, by reusing trimmings of car manufacturing instead of remelting them. We need lightweighting of products to use less steel to reduce emissions substantially. That means smaller cars, more intelligent building design, for example. We also need the longer lived products, and most importantly, we need the more intense use of products. That means a lower car fleet, lower square meters per persons by better building design, better urban design in the future. This will help bring down material production. This will help reduce emissions to sustainable ranges. Overall, our research finds that we need to combine demand and supply side solutions for a low carbon future. That means we need to improve industry. At the same time, we need to transform demand to these before mentioned different urban patterns and leading to different building stocks, co-location of residential, non-residential buildings, lower car fleets, because this will help reduce the dependency on primary production. This will help reducing dependency on fragile global supply chain, and this will help decoupling material use from these substantial and massive climate impact. So our main finding is from the research we've done that lifting material efficiency to the same prominence level as energy efficiency increases the feasibility of attaining the Paris goal of limiting global warming to well below 2 degrees Celsius. So we need both the supply side in the industry and the demand side in the society. This concludes this quick overview of the steel cycle. We offer more exercises, for example, scenario models, and a lot of data sets on our teaching material collection and the industrial ecology data commons. So please stay tuned and have a look. You will find more useful research material from the industrial ecology community on these pages. Thank you.